in a meeting. So but I สำหรับกำลังคิดอยู่นะครับว่าสำหรับคลาสที่มิสไปเนี่ยหรือเราจะทำเป็นแบบคอนเทนต์เนาะทำเป็นวิดีโอแล้วเราก็ทำเป็นควิสเอานะครับเดี๋ยวผมประกาศทางนั้นนะครับโอเคนะครับso that we don't waste any more time let me just actually just one นะครับ okay let me just start it with this one okay so we have reached the topic about the argument, right? So what is argument? Let me remind you a little bit. An argument is a collection of uh, propositions, basically. So you have a lot of like sentences or propositions, and then all these propositions before the end are considered to be what we call a hypothesis, or and just go back. Sorry, let's just go back to this one. Okay. So the argument is a sequence of propositions. So anything that is before the end of the proposition or the final propositions, they are called the hypothesis or an assumption or a premise. Okay. So anything that's before the end will be called premise. And in arguments, we will automatically assume that all the premises are true. Okay, all of them are true. And then the final proposition is called the conclusion. Our job or our task here is to try to check whether the argument is good or valid or not. Okay, so what is a valid argument? A valid argument is that when you consider all these premises, which you all know true, that they are all true, and then if all these premises has uh, has a conclusion that that or you can conclude that your conclusion must be true from considering all these premises, okay, then your argument will be valid. Okay, valid. So if the conclusion has to be true, considering that all the premises are true, then this argument is valid. Okay, that's what we are going to do. For example, I think we have this example. Remember, we have two premises in the example. Okay, the first one is if Iron Man is a man, then Iron Man is mortal, right? If Iron Man is a person or a normal person, okay, then Iron Man is mortal, which means he can die. Basically, he's a human. He's normal human being, basically. Then you have another premise which say Iron Man is a man. Okay, so the conclusion is Iron Man is mortal. So you have to think that okay, the green sentences, which are premises, are assumed to be true. So if you assume these two sentences to be true, can you conclude that Iron Man is mortal, right? I think I explained this a little bit with all this writing. So basically, if Iron Man is a man is true, then the top sentence, which means that these Iron Man is a man is true. Okay, but we know that the sentence, the whole sentence is true. So if this one is a statement, if then, right? Implying statement, right? If then. So if for the if then statement, in order to be true, when the front part or the if part or the hypothesis part is true, the second part or the conclusion part or the after the then part has to be true as well, right? So it's like true if true, right? In order to get true. But if true and then the second part is false, then you get false, right? That's why the second part, because the whole sentence is true, the front part is also true, right? The whole sentence is true. The front part is also true. So you have to have that the second part must be true, which is mean Iron Man is mortal, right? So when Iron Man is mortal is true, then you can conclude that, oh, Iron Man is mortal, which is also your conclusion, must be true. So from this explanation, you can see that these arguments is valid. Okay, this argument is valid. To make it easier, you can see that the bottom example is much easier if you translate all these sentences into a symbol. And then you have Iron Man's man is P, Iron Man is motto is Q. So you have if P then Q and then P for Iron Man's a man, and then the conclusion Iron Man's motto is Q, right? So if you know P is true there. P if then Q is true, then Q must be true. So Q must be true, then you have the conclusion is also true, right? So that one, that show that this argument is valid. Okay. Um, so for the rest of this lecture, we will discuss how we can find or how we determine if any argument is valid or not. Okay. There are two approaches that we can use to check whether or not the argument is valid. The first one is using truth table, which I explained it in the last last lecture. So basically, if you want to check if argument is valid, you have to create a truth table. In your truth table, you have to show or you have to have a column showing the truth value of all the premises, right? For example, in this example, 7, right? You have two premises, P or Q or R, and then you have negation of R. So you will have to have two columns that show the truth values of these two premises, so which is this column 1 and this column 2, right? And then you also have to have a column that show the truth values of the conclusion, which in this case P or Q, right? P or Q there. So just show the truth values there, right? That's this is a conclusion, right? So now the only thing left to do now is to check whether or not it's this argument is valid. So what you're looking for, the next step is you look for the critical role, right? Critical role. What does it mean, critical role? Critical role is a row of a truth table which have the truth values of all the premises as true. Okay, so you basically just look at these two columns, and I look for the row that all these two columns have truth value as true, right? So you can see that, oh, there are row number 2 and row number 4 and row number 6, right? So 2, 4, 6, these three rows are the critical row, right? So 2, 4, and 6 are critical row, critical row, right? So now with these three rows, the final step is to check if the conclusion of these three rows, the value of the truth values of these three rows for the conclusion are all are they all true? Okay, so you can check that number 2, number 4, and number 6, they are true. So if this happens, this means that this argument is valid. Okay, but if there is at least one truth values of the conclusion for one of these critical row as false, then you have this argument as invalid. Okay, so this one clearly is valid. So, answer here. Another example, similarly, you have two premises, which basically same premises as the number 7, and then you have conclusion. This conclusion is different from the conclusion from the previous one. So you look for, again, look for critical row, which you have same row because it's the same premises. So you have row number 2, row number 4, and row number 6. Okay. So these three rows are the critical row. Okay. And then you find the truth value of the conclusion on those three critical rows. Okay. Check them. Are they all true? As you can see, the number 4, the row number 4, they're not true, right? They are, it is false. So this one is, this argument is invalid. Okay. So make sure you are you are able to check the argument is valid or invalid using truth table, because it's going to be in your final, um, which should be easy, I think. Just make sure you be able to create your truth table. Any question on this one? Okay. Now, um, basically, you can just use truth table to find out whether your argument is valid or not. You can always use that. However, because truth table sometimes difficult or tedious to create because it requires a lot of writing. If there are a lot of atomic propositions, you remember the number of row of truth table depend on the number of atomic proposition. So if you have n atomic proposition in your premises, in your conclusions, then you're gonna have to have 2 to the power of n rows in your truth table, right? If you have 2 atomic proposition, that's that's easy, right? You just have 4 rows, right? But you have 3 atomic proposition, you start to have 8 rows, which I still think it's doable. Okay, not that difficult. But if you have, say, 4 atomic propositions, then you have 16 rows. That's it's getting a bit difficult, right? Imagine you will have 5 atomic proposition, 6 atomic proposition. You have 32 rows, 64 rows. I think that's too difficult. Okay, I think my limit would be if you have less than or equal to 3 atomic propositions. I think that's acceptable to use truth table. Okay. But in case you don't want to use truth table, or there are too many rows that you have to create for your truth table, you can use this the second approach, which is called using the rules of inference. Rule of inference. Okay. What is rule of inference? Rule of inference is a arguments that already valid. You don't have to check them. You can use these arguments and then apply it into your own argument to try to check whether or not your argument is valid. Okay, you use all these rule of inference. Okay, and then you try to approach that, or you trying to show that the conclusion must be true. Okay, so what rules of inference do we have? We have a lot of rules of inference. So we have at least, actually there are more, but I think I chose just 7. So we have basically 7 rules of inference. Okay. Just quickly go through with it a little bit. So, for example, rule of inference called addition. Addition. Okay. So let's say that if the premise is P, the conclusion P or Q. So that's very makes sense, right? If P is true, remember, if P is true, then P or with any other proposition will always make that the whole proposition true, right? Yeah, okay. And the second one is simplification. You have P and Q become true, then you can certainly be confident to say that P must be true, or you can say Q must be true because it's connect with and, right? And the whole thing is true, which means that P has to be true and Q has to be true too, right? The second one is P. It's called modus ponens. So if you have P as your premise, if you have if P then Q is your premise, then you have Q as your premise. This is a exactly the Iron Man example. This one. Okay, right. If Iron Man is a man, Iron Man is mortal. Iron Man is a man, and Iron Man is mortal. Okay. Um, the fourth one is modus tollens. This is similar to the one on top. You have negation of Q, and you have P imply Q. Those are two premises, and you have negation of P. Okay. So you just say, oh, this negation of Q is true, then you have Q as false, right? Q as false. Then in order for P, if P then Q has to be true, if Q is false, then can P be true? You cannot, right? Because if P is true, then Q is false, then true, if then false, then become false, right? We don't want that. We want it to be true. So if Q is false, then P has to be false as well, right? If we know P is false, then negation of P has to be true, right? It's the opposite of false, right? So this one is modus ponens. The third one, I mean the one on the right, I'm not going to explain it, but you can use these. I mean, if you see something that you can use, apply one of these, you can use them. You don't have to remember them. Remember that you can always open your book and when you do exam or quiz or anything. Okay. So how do we use it? Can can I excuse myself for half a minute? Okay. So how do we use the rule of inference to validate arguments? Well, there are three steps, three simple steps. But the first one is to identify the premise and conclusion because sometimes the problem doesn't come predefined your premises or your conclusion. You have to identify them yourself. But if the problem comes with like say premise or conclusion or is, then you're lucky. I mean, yeah. But usually it's not like that. You have to identify, oh, these are premises, this is the conclusion, these are not premises and not a conclusion. Okay. So the first step is to identify the premise and the conclusion. The second way is to write down all the arguments. I mean, like all the premise or the proposition in a separate line, okay? And whatever you write down, that sentence or that line is true. You have to make sure that it's true. How can you make sure that? Well, you can use the first one. You can use premises because premises we assume to be true, right? What else we can use? We can use premises combined with another premise and then use the rules of inference to obtain another proposition that we know is true, right? For example, if we know that um, P is your premise, one of your premise, then P imply Q is your premise. So these two premise, right? You can have another proposition that you definitely know true is Q, right? Because this one is modus ponens, right? You remember, right? So we're going to use premises and rules of inference. This is how you can use rules of inference. You identify the the proposition that you think you can apply, and you get another statement or another proposition that you can use rules of inference to say that they are true. Okay, for this example, and you keep doing that until you get closer to the conclusion, until your final step is to conclude that the conclusion must be true. Then your job is done and you conclude that the argument is valid. Okay, but of course sometimes you can, if you cannot conclude if the argument is valid, then you have to say that you probably have to say that the argument is invalid. Okay, so let's see let's see an example. For example, okay, um, let's say that given the following premises, let's say P imply Q, negation of Q or R, okay, and then the conclusion is R. Can you validate that this argument is valid? Okay, we have three propositions or three premises, and we have one conclusion. How can we do this? Okay, I would start off with, remember we want to write a premise or a proposition or a statement, one proposition per line. And then you should have a column that explain why is the proposition or the statement is true. Okay, why is it true? And then you usually have a number that mark like what line number, because we always refer back to all these lines later, so you have to have the number to be easier to refer to them. Okay? So for example, the first line I would write would be P, and then I would say, oh, P is true because P is a premise, right? Then I kind of see something of a modus ponens there, right? Because I have P, I P imply Q, that's definitely modus ponens, right? So I write another one that I would use, that I know I would be able to use it as a modus ponens, which is if P then Q, right? Why is if P and Q is true? Remember, you have to always put statements or proposition that you know is true, right, on the list on this column. Now you have to answer why if P then Q is true. Well, because it is a premise. And remember, we always assume that premise is true, right? So if P then Q premise, yeah, it's true, right? And now from from P, and then if P then Q, and then because of the modus ponens, which I right here, so that I remind myself that how do I get Q? Because I use this modus ponens verb, right? So on to the number three line, you have Q because you have modus ponens P, if P then Q, and then you can conclude that Q is true, right? But our job is not finished, right? Our job is to find if R is true, right? So the second step would be we have one more premise left. So I was just going to write one more premise here, negation of Q or R, right? And because Q we know already true because we write it here, it's true. So I can double negation, right? Negation of Q, which basically mean Q, right? But once I do that, when I do that, I can have one of the rule inference, which call disjunctive syllogism. This one, which is saying that negation of P or Q, and then negation of Q, and then you get P. So this one, you get this one is like P, this one is Q, P or Q, and then negation of Q. Oh, this one is, oh, what is it? Negation of Q or PQ, negation of Q. Okay. Ah, I should write the PQ. I should write the QP, and then this is negation of Q, right? So Q is negation of Q, negation of Q is negation of Q. Maybe it's a little bit confused on the symbol. But once you have this Q or R, or I mean Q or P, Q or P, Q or P, and then you have negation of Q, then you can use this disjunctive syllogism, which is that if you have P or Q and then you have negation of Q, you have P. So I have Q, P or Q, and then you have negation of Q, which I have with which I will have, what is it? Oh, P, all right, which I will have the R, right? And then our job is finished, right? Because R is what we're looking for. So now we know that R has to be true, okay, using this approach. Okay, and I have any question? I think that's it for this slide. Oops. Okay, if no question, I'll move on to the next slide. Hmm? Okay, so the last lecture, if you remember, the last lecture talk about proposition, remember? And with your proposition, basically you're talking about all the sentences that have a truth value, right? Anything, any sentence that doesn't have a truth value, a question, a something that doesn't really have a truth value, you will not be putting those in a propositional system, right? Right? Or we can call it propositional logic, positional logic, right? So how do we make some of those sentences become a statements that have a truth value so that we can use those and put them into a system that we can use, the logic system? Okay. Let's see one example that we say earlier that is not a proposition, for example. This one, he is a university student. Right? This one, if you go back to the propositional statement, propositional logic, you would say that, oh, this one is not proposition because we don't know who he is. He could be a university student, but he can also be something else. It doesn't have to be a university student, right? So this one, for propositional logic, is not. It's not proposition, right? Similarly, x is greater than 3. because we don't know the value of x, so the sentence can be either true or false, right? It can be either, unless we know the value of x, right? We can't tell anything else, right? So this one, again, not proposition. So, but of course, we want to include all the sentence that we found, and then we put it in the system that we can use. Okay, but clearly, the propositional logic doesn't work. Okay, so how we do it? So we will go to the what we call a predicate logic. We will solve a problem of those sentences that doesn't have a truth value. We're gonna put a truth value into it, put something into it so that it can tell us what the truth value is. Okay. First, let's start off with a definition. So when you say predicate logic, predicate actually mean the part of the, the, oh, นะครับ one minute. Ah, นะครับ First, we are going to discuss a little bit or learn a little bit about the definition, okay? So the predicate logic has a part that that is actually a predicate, okay? The basic meaning of predicate mean like a what do you call it, a front part of something, okay? So predicate is something that you add to the front of a sentence, okay, that to make the sentence or the statements become a sentence that or statements that has a true value, okay. So predicate, when we say predicate in um, this area, we say that predicate is a sentence, okay, just like proposition. So when we say predicate is a sentence that has a finite number of variables and become a statement or a proposition when specific values are substituted for the value for the variables, okay. So you add something and then you limit the domain, okay, the domain or the variable, okay. So the domain, we'll discuss the domain a little bit on the function. The domain is basically the set of all possible values that we can use to substitute in place of the variable, okay. Let's see some example. For example, if you have a statement x squared is greater than x, okay, say x squared is greater than x, okay. So these sentence can become a statement, okay, when we say that x is all real numbers, okay, when we say x is all real numbers, okay. So let's say that p of x is the statement x squared is greater than x, where x is all real number. So when we want to check the truth values of p of 2, so p of 2 is 2 to the power 2 is greater than 2, yes, and become true. If p of 1 half, 1 half square is greater than 1 half, no, that's false. P of minus 1 half, so minus 1 half square is greater than, uh, I miss it here, greater than 1 half, minus 1 half. Is it true? Yes, it is true, because minus 1 half square is 1/4, which is positive, is greater than what minus 1 half. Okay. Oops, sorry. Um, mm. So now you're gonna have a different symbol a little bit. Okay, so before you have a small letter, right? P, Q, R, S, T, whatever. And then in this predicate world, you will have a capital letter for a sentence or statement. For each statement, okay, you will also have to have a variable symbols, right? This X, okay. So you have a capital P in the bracket of a small letter x, okay, where x is a variable in the sentence, okay. We call this P of x as a predicate, okay. X will be a domain, which usually we use a domain as a real number, set of real number. X will be called predicate variable, okay. So this one we will say, or we will read it as the set of all x in R such that P of x, okay, where P of x is defined as x squared greater than x, okay. Let's see another definition. So let's say that if P of x is a predicate and x has a domain D, the truth values of P of x is the set of all elements of D that make P of x true when they are substitutes for x, okay? The truth set of P of x is denoted as the set of x, where x is a domain D, P of x, okay? At the set of the truth values of P of x, okay? For example, let's say Q of n, okay? Be the predicate of n is a factor of 8. A factor mean like um, it can divide 8, okay, basically. So if you factor out 8, for example, you can have 8 is 2 times 4, right? You can say 2 times 2, sorry, 2 times 2 times 2, right? For example. And then another one is will be 8, right? Because 8 is equal to 1 times 8, right? That's the factor of 1 times 8, right? So let's say if the domain of this predicate is a set of positive integer, okay, is the set of all positive integer, okay, find the truth set of q of n, okay, find the truth set of q of n. So we want to see, we want to know if what the value of positive integer that will make p of x become, oh, I mean q of n become true, right? You can say that, uh, of course, 1, because 1 is a factor of 8, 2 is also a factor of 8, 4, and then 8, right? That's for the domain A of the positive integer. But for the domain of all integer, you can have 1, 2, 4, 8, minus 1, minus 2, minus 4, minus 8. you can have a negative number as well, right? So that's the domain and the truth set, the truth set, okay, of the predicate. Now, sometimes we have to put on a quantifier, okay. A quantifier is a an wow, what do you call it, a operator that limit of or a a threshold, I think, that limits or that set the line or that set the standard if the statement is going to be true or false, depending on the quantifier that will limit the number that of the domain, right? So there are going to be two quantifiers. The first one is the for some, or we call, I mean for all, I mean, which we called it a universal quantifier, or we may probably heard of them more as a for all, like for everyone. Okay. So a universal statement is a statement using a symbol like this. Okay. The big capital A, but upside down. A capital for all x. So I read this as a for all x. Okay. In the set of domain, okay, q of x, okay. So this is called a universal statement, okay, because it has a universal quantifier for all, right, for all. And then these can be find or can be told if the statement is true or false, right? Because for all excuse me, for all means that every x, okay, in this case every x in the domain. So for the q of x to be true, every x has to make q of x true, okay. So that's the truth value, true, for the universal statements, okay. But if one, at least one of x make q of x become false, then this statement will, the whole statement will become false because it's a for all. So if you miss just one, one not true but false, then this whole statement is become false, right? For example, for all x, in the positive integer z set, x squared is greater than x. For all x, in the positive integer z, x squared is greater than x. Okay, is this true or is this false? Well, if this statement will be true, then every positive integer has to be true for x squared is greater than x, right? You can try to substitute some value. So positive integer x starting with 1, I think 1, 2, 3 up to infinity. So you can substitute 1. Is 1 square greater than 1? Oh, you find an example that is false already. So you can see that, so if x is 1 square is not going to be bigger than 1, right? Which means that this statement is false, right? Right. So this statement will be true if it's all true, right? Every member in the domain, which in this case is a all positive integer, all of them has to be true for q of x, right? Okay. The second one, same thing, same statement. For all x and domain D, x squared is greater than x. But this time, instead of using the domain as a positive integer, right? we use we use a set of D, where D is a set of 2, 3, 4, 5 up to infinity. Okay, up to infinity. Okay. So is it true? As you can see, if you try to substitute 2, 2 squared is 4, 4 is greater than 2, yes, correct. 3 squared is 9, 9 is greater than 3, yes. Um, 5 squared is 25, 25 is greater than 5, right? So as you trying to submit a bigger and bigger number, you see that it's always going to be true, right? The only initial number that is not true is probably 1. That's the only number. But now you don't have that in your domain. So these statements where the domain is 2, 3, 4, 5 up to infinity, then this statement is true. Okay, this statement is true. Okay, any question? Question? Okay. Let's see the next quantifier. The next quantifier is existential quantifier. Okay, the existential, or as we know, uh, as for some, okay, for some. So for some, use a symbol as a capital letter E, what do you call it, flip backward, the inverse of the capital letter E. So you can say that an existential statement is a statement with the existential symbol, the capital letter E inward. And then in the domain D, Q of X, okay? It is true when only one, if only one, I mean, not only one, I mean, at least one, I should say at least one, if at least one of X make Q of X become true. Okay, then that statement is true. But it is going to be false if none of the X make Q of X true. Then it is false, right? So let's say example 9. Consider the statement for some X in the set of positive integers Z plus X to the power of 2 greater than X. Is it true? Well, that's easy because you can just choose one example where X squared is greater than X. Let's say I think I chose 2, right? 2 squared is greater than X. So that's true. So you know that now the number integer 2 will make this statement true. And then it just said that for some, which means that 1 is already enough. So this one statement is true. Okay. But then if I change the domain a bit from the positive integer into the set of 0 and 1, 0 and 1, then you can check. Well, there's only two domain, right? I mean, two members in the domain. So you can manually check using by hand every single one in the domain, which is 2. So 0 to the power 2 is 0. Greater than 0? No. So that's false. 1 to the power 2 is 1. 1 greater than 1? No. So all the members of the domain fell. So which means that this statement for some is false, right? Okay. Any questions so far? No? Okay. Um, okay, I'm just gonna give you a quizzes, short one. Ooh, I think this one too hard. Okay. Or maybe I should let's see, I give All right, let's do short one first, and then and then just a quick and short one. Okay. All right, I'm just gonna um, oops. Okay, let's do a bit of a quizzy. Okay นะครับเดี๋ยว let me show you the quiz that you should join. Oops. Oh, no, this one. Oh, this one. Okay นะครับ you can join now. Remember, please remember to name your uh, name using your ID number and your first name. Okay. Titawat. Titawat is okay. Last name, right? 2120. And the first name Titawat. But if you can use like the full ID number, will be okay as well. Oh, Kun Patikan, can you please put a little bit, put your ID number in? คุณจีรวรรณด้วยนะครับ let's wait a bit. Okay. Okay, 25. How many do we have here today? 27. Okay, let's wait a little bit more. Okay, 30. Maybe we can start a short one. Just to, all right, let's do it. Don't look at my screen. Look at your screen to answer the question. Okay. Which phase that not indicate universal quantifier? Ooh. Universal quantifier. Okay. Um, ooh, I'm surprised. A lot of you answer them. They answer this one incorrectly. So the question asks which phase that not indicates universal quantifier. Universal quantifier is for all, right? So the first one is definitely that's the direct phase that we use for universal quantifier for all. And if you use for every, I think it's the intention, the meaning is almost the same, right? The hard one would be for each. For each also used, normally used for to mean that for all as well, right? So for all, for every, and for each. Okay, these three are a common phrase that we use for universal quantifier. Of course, the for some is definitely incorrect, right? Okay, maybe you misunderstood the question because it's a negation question, right? It's not indicate. Okay. Ooh, okay. So a lot of you now can, I could see that most of you now be more careful of answering this one because which phase not indicates existential quantifier. So for existential quantifier, we means for some, right? So the for some answer, the last one, that's definitely not, right? That's definitely existential quantifier. The exist also we use as for some, okay? The exist means like there's one, okay? And then there is a referring to there exist. There is one that da 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 da, right? But for each, from the last question, you know that for each mean that universal quantifier, okay? Uh, well done for 16 of you. And next question. Ah, ooh, well, change. Okay. So all is a phase that indicates what? Universal quantifier, existential quantifier. So all mean, of course, universal quantifier, right? I mean, for all, so all indicate a universal quantifier. But if you use the word like some, then that's existential quantifier. Okay. The next question. Hmm. Okay. I feel that people who sit down, listen to the lecture earlier should answer this one. So the symbol for existential quantifier, okay, definitely is the first option, the first choice, right? So it's a E, but it's like flip, like not backward, but left and to right, right? So this symbol, okay. Other symbols are not for existential quantifier, okay. You can remember is that existential, so start existential, start with E. So the symbol should be E, but it's flip, backward. I mean back, like a inward something. Next one. Oh, okay. I feel that a lot of people will answer this one correctly. Maybe a little bit of confusion. So the symbol for universal quantifier, so for all, it basically, you remember for all, the word all. So it's like a capital letter A, but upside down, right? So yeah, that's quite easy. So next one. Oh, okay, this one. I'm surprised. There's two people answering it wrong. Maybe intentional. Okay. So, well, I mean, every is a phrase that indicates what? So every, it means like everything, everyone, every dogs, every butterfly, every flowers. So of course it's for all, right? When we think about for all, it's a universal quantifier, right? So yeah, most of you got it correctly. So okay. Uh, Next one. Okay. Leaderboard. Ooh. So some, right? When you talk about some, it's like for some. So it's definitely existential quantifier. Okay. So last three questions. So there exists is a phrase that indicates, of course, existential quantifier, right? I think you're getting there, getting there. They exist, right? When there exists, right? Just one or some that exist, it means like some, right? So we talk about existential quantifier. All right, last two questions. Okay. So this, well, the question is a bit unclear, but I think it's saying that let's the symbol M of X represent the statement X loves mathematics, right? Where X consists of all students, okay? Where X could, indicate all students. So basically, they want you to translate this symbol, this sentence, this statement into a English sentence, right? So the first one is all students love mathematics. Okay. Some students love mathematics. There exists students love mathematics. There is a student love mathematics. So you can see that X consists of all students. So we're talking about all students that love mathematics. So the first one is the most correct one. And the last question. This one is a little bit of a trick question, right? Basically, the question is the same, right? That's m of x is equal to x love mathematics, where x consists of all the students, right? So which one is, which one? Oh, translate. I forgot to translate. Translate the exists negation of m of x into English sentence. So there exists, and then you put negation of m of x, right? So there is someone who doesn't love mathematics, basically, right? If you translate it directly, right? There exists someone who doesn't, because m of x is love mathematics. So negation of m of x is doesn't love mathematics, right? So the first one, there is a student who is who does not love mathematics. Okay, the is so this one is correct. Let's see the second. There is a student who love mathematics. That one is incorrect, right? All student does not love. That one is incorrect because it just says someone. All student love mathematics. That one is incorrect too. So okay. Ooh, many of you answered the second one. Okay, I wonder why. The second, there is some student who love mathematics. There is some, well, because there is a negation. Oh, I forgot to put. Okay. Maybe you're confused about this symbol, right? This symbol is a negation symbol, right? If you remember in the propositional logic, this one means that it's a negation of the sentence. So if m of x is love, negation of m of x is doesn't love, basically. Okay, so the first one is correct, and that's it. Um, let's see the winner for today quiz, which I can't read the name because it probably meant to write it in English, but the layout was in Thai, right? So congratulations to 476-6. Oh,
ขอบคุณ
already
ครับ
answer wrong one question. Well done. คุณธนากรนะครับOoh, the first one is incorrect. And then คุณธีระเดชนะครับ the top three. Well done. Okay. Let's exit. This one. Okay, the last 12 minutes. Okay, let's just go back to the slides a little bit. And mm, okay. So now that we learned a little bit about existential and the universal quantifiers, okay, let's say that if we want to translate some English sentences or maybe some Thai languages, some Thai sentences into into a predicate sentence. How can we do it? Okay. For example, if you want to translate this sentence, all triangles have three sides. Okay. All triangles have three sides. Okay. So in order to translate this, first you have to identify what quantify, or well, first you have to identify how many variables is there in the sentence. Okay. How many variables mean like how many objects in this variable. Okay, so this one you can clearly say that they are talking about triangle. Okay, even though it's all triangles, so we're just gonna count as one variable. So this one can be used as x. Okay. Now the second step would be to identify which quantifier will you use. So in this one, it's clearly say or, right? So basically, you're gonna have to use a for or the universal quantifier. So you can say that let's P of x, okay, P of x be the sentence x has three sides, okay, x has three sides. X can be anything. Then you have to kind of put the domain into that. So let's say that set T is the set of all triangles, is a set of all triangles. So your sentence would be something like this. For all x in the set of T, set of all triangles, P of x, which means x has three sides. Okay. X has three sides. That's the predicate sentence. No question. Okay, let's go to the next one. What about some dogs have wings? Again, we first, similar to the last one, we just identify how many variable. It's just probably one. That's this dog. And then the next one, quantifier, which one should you use? It's sum, so it's the axis or existential quantifier. And then you can use Q of X, X has wings, and then D as a set of all dogs. So then you can have the axis X in the set of D, Q of X. Okay. X is a dog, and then X has wings, basically. That's what I'm saying. And this one a bit harder. Okay. Let's say this one is if a real number is an integer, then it is a rational number. Okay. If x is a real number, I mean, if x is a real number, is an integer, sorry, then x is a rational number. Okay. So let's see. First, identify how many variables. You can see, oh, there is a number there, right? A number there, but I think that's it. Yeah, right. That one is x. So should we use for all or for some? This one doesn't specify like for some or for all at all. So when there is a sentence that doesn't say like for some or for all, we usually assume that it's for all, which means the statement must be true for all x. Okay. So this one we can use for all. We can use x, and we can say like, let's say p of x is uh, uh, x is an integer, and then q of x, x is rational. Okay, so the statement that we're gonna use is for all x, okay, p of, oh, let's say, oh, I forgot about the domain, right? Domain, well, I can say that let's say the domain is the real number. Okay, so any real number, if x is integer, well, some real number is also integer, right? Then uh, q of x. So let's say the real number. Okay, for all x in the set of R, p of x imply q of x. Oh, I can say. just to make it shorter. I mean, to make it short, scope smaller. So for all x in the set of integer, p of x, which means x is an integer, then q of x, x is a rational number. Okay. Okay. Last two example. let's say now backward. If you have like a predicate symbol, you want to translate back to English, what do you do? So this one say for all x in the set of real number, x squared is greater than or equal to 0. So you can just say that for all x in the real number, x squared is greater than or equal to 2, right? You can say something like this: for all real number, the square is greater than or equal to 0, right? So it's basically the same thing. The square of any real number is non-negative. You can say something like that, okay? Next one would be there exists x for in the integer x squared is equal to x, okay? So you can say like there exists x as an integer, x squared is equal to x. You can say something like there is an integer whose square is equal to itself. That's informal, right? For some integer x, x squared is equal to x. You can say something like that. Okay. Okay, I'm just gonna stop here. Any questions so far?
ไม่มีครับ
ผมสอนต้องบอกว่าเนื้อหาพวกนี้จริงๆผมสอนกับเด็กวิศวะหลักสูตรปกติด้วยนะครับ แต่ทุกครั้งที่ผมสอนผมจะมีความรู้สึกว่า เนื้อหามันไม่ได้ยากนะ แต่ว่าภาษาอังกฤษมันจะเขาจะไม่ได้ ผมรู้สึกมั่นใจกว่าเวลาสอนกลุ่มเรานะว่าเราน่าจะได้ภาษาอังกฤษนะไม่รู้แอสซูมมาเองว่านะยังไม่ได้ตรวจมิดเทอมเลยนะครับเดี๋ยวไปดูตรวจมิดเทอมว่าจะได้ไหมโอเคนะครับถ้าไม่มีคำถามวันนี้ก็เท่านี้นะครับเดี๋ยวเจอกันสัปดาห์หน้านะครับขอบคุณครับ
ครับ
ขอบคุณค่ะ
ขอบคุณครับ
เอ็ดคิว